Hello everyone, let's go ahead and wrap up chapter 3 by doing 3.8 and 3.9. One thing to note is there will be no homework over either of these sections, and I will not be testing over them, but they are something very useful, technically useful tools for particularly approximating values like roots, or just approximating values generally, approximating differentials. So 3.8 is on Newton's method. So as times, finding zeros of functions, especially roots that are not values or not rational values, irrational ones, can be tedious, and aside from, say, the quadratic formula, it's hard to kind of approximate them. But calculus has a way now of doing this, regardless of, the powers, called Newton's method. To see how Newton's method works, what we kind of do is we look for the function continuous on an interval, and we use a tangent line at a known value to approximate where the root would be. And then when we overshoot or undershoot our root, we redo the tangent line from now a closer point until we kind of zero in on an approximation for the root. Now, point slope form for a line is y minus y1 equals m times x minus x1. We're just replacing y1 with f of x1, and replacing m with the derivative at the particular point, and that gets us y equals the derivative times x minus x1 plus the y value. But since we're looking for zeros in particular, we know y equals 0 in this equation, and then I can solve for x by moving f of x1 to the other side, dividing by my derivative, and adding the x1 to the other side, and you get this. The new x approximation is equal to our original x value minus the y value at that point divided by the derivative at that particular x value, and that's called Newton's method. So you let f of c equal 0, and where f is differentiable, make an initial estimate close to where your root is, either a graph or just generally knowing the equation is helpful, and then you get a new iteration of x, a closer value each time, and each time you apply x, you get closer and closer to what the root is. So we're just going to look at how this looks in one example, because we're not testing over it, to see how this would be useful. But you may recognize, as in the era of calculators, this becomes somewhat less useful, but it's still a good technique to know when you come about it, knowing how the tangent lines can help us do things. So calculate 3 iterations of Newton's method for the function x squared minus 2 with initial estimate of the root x equals 1. Now we know that this root is going to be plus or minus the square root of 2 because we could solve it if we set it equal to 0. But let's see how Newton's method works. My initial guesstimate x1 is 1. Okay, so what I need to do is I need to plug in this x value to the original function and to the derivative. If I plug it into the original, f of 1 would be 1 squared minus 2. 1 minus 2 is negative 1. What's the derivative here? It's 2x. What happens when I plug in 1 there? 2 times 1 is 2. Now, according to the formula, I need to divide these two things. So that would be the first column divided by the second column. So f of xn divided by f prime of xn. Negative 1 divided by 2 is negative 1/2. And then ultimately, I need to take my original and subtract whatever this is. 1 minus negative 1/2 would be 3/2, or 1.5. Since this is an iteration, that means my next starting one would be 1.5. And you continue to repeat this process. Now I have the table of what this actually ends up doing in decimal form down below, because it's kind of expected that you would have a calculator or some kind of machine to help you run these calculations. What you see is the process continues by plugging 1.5 into each of these things, subtracting off a piece. We keep going, and we finally arrive at the 4th iteration. So I've gone through 3 iterations, and I arrive here. Now, if you put the square root of 2 in your calculator, you notice that this is actually very, very close to the square root of 2. And so this is kind of a technique that helps us approximate values for things that we couldn't have approximated before. So it is kind of an interesting technique, but I recognize that in the era of calculators, maybe not super applicable when you could just find the roots in the calculator. But it does inform you how the calculators get their decimal approximations as well. Now 3.9 is a little bit different. It's called differentials in our error propagation, but it uses the same kind of idea of the tangent line. So when the tangent line to the graph of f at a point c comma f of c, we know again, it's the y value plus the slope times x minus that x value. It's used as an approximation for our quantity. It creates delta x, the change in x, or delta y, the change in y. So we can kind of approximate those. Now what we know though is when delta x is really, really small, the approximation becomes the derivative at that point times delta x. And for that approximation, the quantity delta x is traditionally denoted by dx and is called the differential of x. And the expression f prime of x dx is denoted by dy. So when you take the derivative of y, you get the derivative of the function dx. So that's our definition of differential. We're kind of used to normally it looking like dy dx equals f prime of x. So what this is really going to end up looking like to you is we kind of multiply the dx to the other side. That's not actually what happens, but it is visually what kind of it looks like what happens in the equation. And generally speaking, as delta y and delta x go to 0, we really become dy and dx. Now, how can we see how accurate this is using this formula? Sure. It's kind of used as an estimator for values. So let y equal x squared and dy, find dy when x equals 1 and dx equals 0.01. Compare this to the actual value of delta y at those when x is 1 and delta x is 0.01. So what is the derivative of y? dy equals 2x dx. We just take the derivative. Now what is dy when x is 1 and dx is 0.01? Well, that would be 2 times 1 times 0.01, which is 0.02 by my math. Now that's saying that if I move off of this equation from 1, 0.01 to the right, my value should roughly increase by 0.02. Well, let's see how accurate that is. If I wanted to find the change in my y value, I need to find the difference between 1.01 squared versus 1.0 squared, our original, or 1 squared. Now what is 1.01 squared? It's 1.0201. 1 squared is 1. So really the change in y here would have been 0.0201. Now if we look at these two things, are they very close together? Yes. So this is pretty accurate, as you can see. The way we can describe the inaccuracy is called the propagated error, which is, again, the difference between these two things. The delta y is what we call the propagated error. And that means that if I wanted to find the propagated error here, I could take what I expected, the actual difference, minus the expected difference to get the relative error, what's going on in the problem. So how can I use this to solve some word problems? Well, it's really more about estimating, figuring out what is going on in the problem in particular and trying to estimate it as much as possible. So let's try to do this in a word problem. The measured radius of a ball bearing is 0.7 inches, as shown in the figure to the right. The measurement is correct to within 0.01 inches. So this allows, some margin for error, especially in manufacturing. That's important. Estimated the propagated error in the volume of the ball bearing. Now, why would they want to know the difference in the volume of the ball bearing? Well, materials are usually sold or created or weighed based on their volume, so you may want to know what the potential ranges of weights you could be having on this ball bearing, so what you need to be able to, the arm needs to be able to hold. So as a reminder, the volume of a sphere is 4/3 pi r cubed. Now, we know that our delta r, our possible error, is 0.01 because it's within 0.01 of an inch. Now, if I want to take the derivative of both sides. I can take the derivative of both sides here. We know that the change in volume, dV and delta V, are roughly the same. So dV here is the derivative of this. The 3's will cancel. It will be 4 pi r squared dr, because we're taking the derivative of r. So again, this is this application of differentials. And then I can just kind of plug it in to see what values I have. I know r in this case is 0.7. So 4 pi times 0.7 squared times my 0.01. It could be in either direction, plus or minus 0.01. And if I multiply all these together, get it in a calculator, this is approximately 0.06158 cubic inches cubed. So what that's saying is that the volume could have an error of plus or minus 0.06 cubic inches. Now, if you want to know the relative error, if I look at the actual volume of the original, if I wanted to plug in my radius to the original, 4/3 times pi times 0.7 cubed, this can kind of give me an idea of where the relative error that I've got. So if I put this into the calculator, this tells me what the expected volume of the ball would be. So when I do this, this thing is about 1.43675 cubic inches. And if I wanted to know the relative error of this thing, I could take my error and divide it by my original, so the 0.06158 divided by 1.43675. So I take, this is my error, divided by actual. It's approximately 0.04286, we'll go with that, which represents 4.286% error. And so this could be positive or negative. So our volume could be bigger or smaller by up to about 4%, as long as my measurement's within 0.01. It's not a huge difference. So generally speaking, this is just a general useful way to find possible errors. And like I said, there's going to be no homework on this, and it's not going to be tested, but it is useful for approximations. And this is really all for 3.8 and 3.9.